So now I will give some motivations for homotopical geometry. Okay, so the first subject will be derived smooth manifolds. And I also will give a reference. So this part is mainly based on the paper by Grisha Taroyan called Simplicious approach to derived manifolds, I think. So initially it was based on the paper by David Spivak on derived manifolds, but this is somehow a simplification of Spivak's approach. So Spivak used, well, I will not go into the detail of why it is a simplification, but basically, if you know all this, think why sheaves are not that popular in differential geometry, at least in classical differential geometry, because you can always replace a sheaf by its global sections via partition of unity. So basically, a paper of Grisha Taroyan is about replacing Spivak's approach by global sections of Spivak's approach via partition of unity. So that's kind of a simplification. But since I'm not given any definitions from the original paper by Spivak, I don't think that it is relevant to my talk. I just wanted to clarify the relationship. Okay, so we start from the following concept. We start from C-infinity rings. So let C-infinity be a category with set in the set of objects indexed by non-negative integers. So we can think of it like this. So we have R0, R1, Rn, and so on. So those are the objects of the category, and tautologically, not tautologically, but by definition, home spaces of, or better, home sets of this category are just sets of C-infinity maps from Ri to Rj. So here I better write it like this. Yes. So what is a C-infinity ring? Well, C-infinity ring is just a product preserving functor from the category C-infinity to category of sets, product preserving. So obviously, I did not mention a very important fact about category C-infinity. So category C-infinity is generated by R1 because we have an isomorphism in this category. That's just by definition. So it's like written into the definition of what a C-infinity category denoted by C-infinity is. So we have this isomorphism. And so A should preserve this product structure on this category C-infinity. And if it is a product preserving functor, then it's called a C-infinity ring. So what's the reasoning behind this definition? Well, first of all, we can recover a ring here. We can just take a set which corresponds to object R1 And so that's support of A. So basically now to endow it with operations, we just need to consider a morphism from R0 to R1, which maps 0 to 0, 0 to 1, and we will get 1 and 0 in this ring. To get operations like addition, multiplication, subtraction, we just need to consider value of this functor on maps from R1 times R1 to R1. So since it's product preserving, I can write it like this. And now we get here, if we write this for addition, this for multiplication, we get all those operations on C infinity ring. And of course, the main thing about C infinity rings as opposed to rings of polynomials, for example, where the similar construction can go through, is that for C infinity ring, we should be able to extend any smooth function on generators to a smooth function on the ring. So, for example, I can consider an arbitrary smooth function from Rn to R1, and I should have a similar smooth function, similar map from n copies of our ring to this ring itself. So if we consider only polynomial maps instead of all smooth maps, then we get just the definition of a ring of polynomials. So that's the basic idea. Okay, but why I'm talking about this? So we can form a category C infinity R, category of C infinity rings, which are by definition just product preserving functors from category C infinity to category of sets. Of course, what we have now, well, we have a forgetful functor from C infinity R to set, which just takes an element here and maps it to this set, which I called support earlier. So we have a left adjoint to this functor, so that's forgetful functor. We have a left adjoint, which I will denote like this. It's a left adjoint to EQ. How does it work? So basically, given as a set, we take C infinity of R to the power of S, which is by definition ring of finite C infinity functions on Rs. What does it mean for the function to be finite in this session? Well, simply, if we have a function from S to R, it is called finite. If we have a finite subset in S, such that this function factorizes into the following composition. So we have a projection from S to its finite subset, and then we have an induced, we should have an induced function from F to R. Then the function F is called finite. So we have left adjoint to this function. Okay. Now I will give a very standard, well, very expectable definition. I'm not sure that it should be called standard, but C infinity ring is local if there is unique maximal ideal M in A such that the quotient is isomorphic to R. So the basic example of such C infinity ring is just the ring of germs of smooth functions at 0 on Rn. So that's an example. So that's an example of local C infinity ring. I think a prototypical example, really. Okay, so now I will give a definition. So that was kind of a definition here. Here. So that should be called definition. So another definition is that of finitely generated C infinity ring. So by definition, C infinity ring is finitely generated. It's finitely generated if it is a quotient. Okay. It is a quotient of C infinity functions on some finite space Rn. Okay, so we will denote by L the full subcategory of finitely generated C infinity rings. Now I'm ready to get some geometric meaning out of C infinity rings. So another definition. C infinity space. So rings were like C infinity rings were like our commutative rings, and C infinity spaces are like affine schemes to us. So the definition is very similar to that of an affine scheme. C infinity space is a pair x of x where the first x is Hausdorff. Second of x is a soft sheaf of C infinity rings on X. So a soft sheaf is a sheaf which allows continuation from closed subsets. Extension of functions from closed subsets. And the final condition, which involves totality, is that for any point P of X, the local ring, well, that's just a fiber of a sheaf of X, really, should be a local C infinity ring. Now, so that was sort of a classical story. I mean, C infinity rings are not that popular, but they appeared like in the 80s, maybe even earlier. So that's here there is no homotopic theory. And to bring in homotopic theory, we just consider simplicial stuff, as is very customary. So now I will talk about simplicial C infinity rings. Maybe there are some questions so far. Or is everything clear and I should speed up? Okay. I saw some faint reaction. Oh. Okay, great. So simplicial C infinity rings. We can just, by definition, consider the category of counter variant functors from simplex category to C infinity R. So that's the notation I use for delta op. Well, since we have a forgetful functor to sets, this simplicial category or has a natural structure of closed simplicial model category. That is not very hard. We just use the forgetful functor to define what are equivalences and fibrations, for example, and then we get the rest of the structure just by using the lifting properties. So that's just from the fact that we have a forgetful functor. Now we can define what are homotopic groups of simplicial C infinity rings. So assume that we have a simplicial C infinity ring, A dot. And so its homotopic groups are just homology groups of the following complex. So M of A is the Moore complex. Since we had a simplicial C infinity ring, then we can totalize it and obtain differential graded algebra, which will compute of which we can take homology. So let me write it explicitly. M of A is a direct sum of components of A with the following differential. Okay. So that's the definition of the Moore complex, and we have homotopic groups of simplicial C-infinity rings. Now I can define what is a simplicial C-infinity space. So X should be once again Hausdorff topological space, and O dot X should be a sheaf of simplicial C-infinity rings. Okay. With one additional condition, that if we take pi 0 of the whole thing, then we get a usual C-infinity space. So pi 0 is obviously C-infinity ring. And so it makes sense to require that something is C-infinity space. Now, I think that we can visualize what is happening here. Basically, the idea is that we have some C-infinity space, and for each dimension, for each simplicial dimension, we just add a certain order of infinitesimal data to it. So that's the basic idea behind direct geometry, that we have an ordinary object to which we add an infinitesimal data in the normal direction. So basically, that's the idea of how we're working with these simplicial C-infinity rings. Now, I want to explain why this formalism is useful at all. Okay. So simplicial C-infinity rings, as well as simplicial C-infinity spaces, are closed model categories. Moreover, they're not only model categories, they're simplicial model categories. Meaning that they additionally have a structure of simplicial category, which is compatible with model structure. So that allows us to compute various homotopy various homotopic colimits. And so, for example, the initial motivation of Spivak's paper was an idea that we want to compute cobordism. We want to compute cobordism ring using no transversality arguments. So we want to intersect submanifolds which are not transversal. And this turns out to be possible using derived geometry. So consider a ring of derived orientable cobordisms of space X. And in order to compute an intersection of two such derived guys, we just need to take a homotopy limit or homotopy fiber product over this space X. So since we're able to, actually, I can note that it is not important that the structure, that we have a structure of simplicial model category. It is sufficient to have only a structure of model category, because this kind of diagram is very simple, and we can define homotopy limits and colimits for it using just a structure of model category. So we just need to make a vibrant replacement, and then we will obtain the homotopy limit. But more on that later. We, of course, will recall all this sort of things I'm saying now, but since it's just a snapshot of what is common, I'm not giving a definition of homotopy limit right now. But it explains why we need them. So in order to compute intersection and cobordism, so in order to compute this class, we need to compute certain kind of homotopy limit. So that is the reason why we need homotopy theory in differential geometry. And so one of the main theorems by Spivak is that actually there is no difference between cobordism ring of derived manifolds and the usual cobordism ring. So when we compute this derived intersection, we in fact compute the real intersection. And so that is useful to basic cobordism problems. So that's one kind of motivation. I think that's it for the subject on on derived manifolds. I kind of explained how we'll need this homotopy theoretic machinery for some concrete problem from differential geometry and topology. Another story that I wanted to tell was about Graphenetic topologies. So it is sort of starts from where we finished here. So here we really got lucky that we can formulate in concrete terms what does it mean to get a derived smooth manifold. This is due to the fact that we have very concrete objects, C-infinity rings. They're very easy to handle because of, for example, partition of unity. And so we don't need this highbrow machinery of general Graphenetic topologies, but sometimes we're not that lucky, and I will give a classical example from algebraic geometry why we need Graphenetic topologies in general. Okay, so an example goes like this. First of all, we get all schemes from affine schemes, which are just duals to category of commutative rings by taking sheaves with respect to Zariski open coverings. So that's basically, we already have a Graphenetic topology here, but I can explain it in simple terms. Sheaf condition is a certain condition of gluing over a covering. and we just call covering maps with open image. Just inclusions, open inclusions of subsets in Zariski topology. So that gives us a notion of a covering, and therefore we can write down a Schiff condition. However, it turns out that Zariski topology is not that useful for some of the problems of algebraic geometry. For example, it is very natural to ask the following thing. We have a functor of K-theory on X being some scheme. So that's just K-theory, meaning that, well, we can think of X as an affine scheme, first of all. Then it's just a K-theory of the corresponding ring. So K of X is K of global sections on X. So that's just algebraic K-theory, which was defined by Quillen. But also we can think of this another way. We can think of it as okay, so sorry, I don't think that this is relevant here. We just can think of it as a usual K-theory, meaning that we consider vector bundles and the difference construction. So it is very natural to ask if the functor K of X is representable in the category of schemes. The category of schemes. So the answer is no, it is not. Similar question can be asked about, for example, homology. So we can take, for example, check homology of a sheaf with a trivial sheaf, and it is well known that in Zariski topology, the answer is always trivial for star strictly greater than 0. So that's called the Graphenetic Theorem, and that's another reason why Zariski topology is not very good, because usually we're expecting to compute cohomology with positive coefficients and get some meaningful information about the space. Here we don't get any meaningful information. So that is why it is beneficial to consider other topologies on affine schemes. For example, there are two most known topologies, I think. So there is et al. And Nisnevich topologies. In affine schemes. So first of all, a map of schemes is called tau if it is if f is flat and unramified. So both conditions can be formulated over an affine subset. And so being flat is just meaning that it gives a flat extension of modules, and being unramified, well, basically it's just a geometric condition, meaning that, well, I'm not a great specialist in algebraic geometry, so I will say what that does mean in characteristic 0. And in characteristic 0, it just means that we have the same number of points in each fiber. So we have something like this and not something like this. Okay. So what is an étale covering? Étale covering is a collection of maps from x alpha to x, such that for any point, not necessarily closed point, x in capital X, we have y in x alpha such that u alpha of y is equal to x. So that's a condition. So that's a definition of étale covering. Similarly, Nisnevich covering. Sorry, first of all, Nisnevich morphism. It's an étale morphism. And second, it should induce an isomorphism on fields of on residue fields at points. So we have a morphism from x to y, and for any y in y capital, we have x in x capital such that k of y is isomorphic to k of x. So conditional covering, so that's the definition of Nisnevich morphism. Nisnevich covering is a similar thing to étale covering. And is a family. Well, it is not. Yeah, it's very similar to étale covering. So we just write the condition for étale covering and assume that all maps in the covering should be not étale but Nisnevich. So what is the point of Nisnevich?
What is H?
H. H. It's not H. It's K, and it's residue field. So.
I see.
Yeah.
Thank you.
It's okay. Thank you for the question. Okay, so what's the point of Nisnevich topology? Unlike étale topology or Zariski topology, it turns out that k of x is actually representable by maps to some spectrum. So here we consider homotopic classes of Manifolds homotopic theory, and it works in Nisnevich topology, and it does not work in étale topology. So that's the benefit of introducing new topology on schemes. Once again, I am not ready now to explain how Manifolds homotopic theory works, but we just can accept that there is some homotopic theory for schemes, which gives us this result. So that's an explanation why we may need various topologies. And actually, we can consider these topologies not on a regular category, but on a model category. So let me give a proper definition of Graphenetic topology, but not for regular categories, but for model categories. So definition. Graphenetic topology. Okay. So let M be a U small model category, meaning that U is some universal set and M is an element of this universal set. So basically, we can think of M being small, or if we don't want to bother with it, we can just think of it as of M as an arbitrary model category, because we can enlarge this universum as we go. So a topology on M is a datum. First of all, a topology tau. For any x, an object of M, we should have a collection of covering families for this object. So it's a set of families in homotopy category of M over X. They are called T covering families. And they should satisfy the following three conditions. So if one wants to, well, I will say this later. Okay, so the first condition is stability. For any x and m and any y from any morphism from y to x, isomorphic any morphism which is an isomorphism in homotopic category of M, this morphism should belong to the set which is formed from this morphism should belong to the set of covering families on X. So that's condition number one. Condition number two is composition condition. And it basically says that if we refine a covering, we still get a covering. So consider UI, consider a set of morphisms from UI to X, which are in the set of covering families, and let for any small I, Uij be a covering of UI. Then this covering Uij over all Inj is a covering of X. Finally, the third condition is called homotopical base change condition. And that's, I think, the trickiest one, homotopical base change condition. So under assumption that 1 and 2 are satisfied, for any covering UI to X, covering of X, and any morphism from Y to X in homotopic category, the family consisting of homotopy pullbacks of these UIs forms a covering of the object Y. So in order to get an ordinary Graphenetic topology, we just need to think of everything here happening over for example, discrete model category where like the only weak equivalences, vibrations and co-vibrations are isomorphisms. And then what we get is the regular definition of Graphenetic topology. Or equivalently, we can just consider the first two conditions, and for the third condition, we can just write just regular pullback instead of homotopical pullback. Okay, so an example of such definition let K be a field of characteristic 0. Let M be a model category of commutative differential graded, non-positively graded algebras over K and opposite, because algebras, because if to get spaces, we want to take the opposite of the category of algebras. So M has a model structure. Let tau be a Graphenetic topology on schemes. So I introduced like 3 Graphenetic topologies on schemes. Let tau be one of them. So we may define a strong topology, tau strong on M by saying that B to AI notice the opposite direction, which comes from the fact that we consider it in algebras in M op, which is equal to CDJ non-positively graded over K. So this thing here is in gives a covering in the sense of tau strong topology if it satisfies the following conditions. First of all, spectrum of 0 cohomology to spectrum of 0 cohomology is a tau covering. Because those are just regular affine schemes. And second, for any index I, we have an isomorphism like this. So that's basically an example of Graphenetic topology on a model category, and we will do something like this when we arrive at higher topoi. We will just consider some categories of sheaves and then higher sheaves, meaning sheaves of spaces on model categories. So those will be changing the base category from regular category to model category corresponds to considering derived situation and replacing the value category, the range category of a sheaf with category of spaces means that we will consider stacks. So basically, at the end of the term, we should be familiar with what a derived stack is. So that's the plan. Actually, I think that well, I can start talking about n categories, but I don't think that it will be wise. So I think that we should end our talk here today at this point. And next time I will start from explaining how higher categories come into play in Galois theory, following an exposition by Bayes and Dolan. Thank you very much for your attention. I will switch the record now. The recording off. Yes.